Happy day. This is Mrs.E.Ponmalar, Associate Professor of Computer Science, the Standard Fireworks Rajaratnam College for Women, Sivagasi. I am here to present the information regarding sum of subsets problem solving using backtracking. This comes under the heading 23 USC 21 Data Structures and Algorithms course of our BSc Computer Science. Now, in data structures and algorithm, we are having backtracking as a technique, and I am going to explain you how some of the subsets problem can be solved using backtracking. The procedure that we are going to follow is, first we will see about backtracking, the basic idea of backtracking, then what is meant by a state space tree, and then we will particularize it to sum of subsets problem and see the algorithm with example to solve the sum of the subsets problem. So, what is the backtracking technique dealing with? The backtracking technique deals with constructing the solutions by selecting a partially constructed solution and develop it without violating the constraints of the problem. So, how we are going to finalize the constraints? If you consider the state space tree, the starting state space tree consists of a single node representing the state of the problem. Initial state, we will be having the node with the root node containing empty set, and then we will make the choices. So, from the initial state, we can have two choices. So, left side we will be having one tree and right side we will be having another subtree. The left side represents the first component of a solution and the right side represents the second component, and it goes on. So, in a state space tree, we will be having each node representing the state of the problem, and the node can take two values. One is called promising node and another one is called as non-promising node. So, when we are going to select the promising node, we will be going on expanding the constraints, and if it is non-promising node, the constraints are not satisfied, so we will stop with the problem. Now, what is subset sum problem or sum of the subsets problem? Let us assume the given set of elements are 10, 7, 5, 18, 12, 20 and 15, and we are given another input which is the target, which is called the sum value is 30. So, what is the problem? The problem is finding all possible combinations of the subsets which gives the sum equal to the target value 30. In this example, for example, we will consider the set 10, 7, 5, 18, 12, 20 and 15. Since the target is 30, the first element 10 plus 5 plus 15, it gives the target 30, and the another subset 10 and 20 adding up to 30. Similarly, 7, 5, 18 adds up to 30 and 18 and 12 adds up to 30. The remaining combinations are not going to give the target value. So, when you consider this, it is called as a non-promising node where the target value is not achieved. So, we will backtrack and proceed in such a way that the sum of the subset always gives the target. So, summarizing the sum of the subsets problem, it is nothing but finding a subset such that the sum of the elements equal a given target. Now, where lies the backtracking approach? The backtracking approach is going to generate the permutations in such a way that the sum of the total becomes equal to the target. But in the non-promising nodes, we won't generate the left child and right child, so that the combination says that we cannot lead to the solution in this point. So, it will backtrack and come to the next promising node and go on. So, it is going to be better than a recursive solution. So, what is the algorithm? The backtracking technique for sum of the subsets problem is starting with an empty set, as I told, representing the initial state of the problem. Now take each and every element and first add the first element, for example 10 from the list of items in the set. The value number 10, if I am going to add it with the initial set which is empty, 0 plus 10 it will be 10. 10 is not equal to 30. So we are going to come to the next. From 10 it will be taking the next value 15 if you take, consider. So 10 plus 15 is 25. If the sum of the data here it is equal to 25 which is not equal to 30. So what we will do, we will come to the next. Suppose I consider the next one as 7, the sum of the total of these three numbers, it exceeds 30. So what we are going to do, we backtrack. So this is the combination that we are going to follow in backtracking technique. Now the subset actually is having two options. One is the sum of the subsets for covering all the elements in that path. If it is less than D, then you are going to backtrack. Another one is, because it is a non-promising node. Another one is if the sum of the subsets becomes greater than 30 also, or in our example it is 30, variable is D. So if the sum is greater than D also, it is not a promising node. So we will backtrack in both these combinations so that we will stop when we reach the values, the sum of the numbers being equal to 30. So this is represented by the state space tree. We will select the working example of the numbers 3, 5, 6, 7, and now the sum of the elements, the target we need is 15. So consider the root of the state space search tree. So here it is equal to the starting point with no value, that is empty set, so 0. Now we will select the number 3. 3 if I am going to select, we will call it as A1. So we have two options, including 3, that is A1 in the left. The right child is not including 3, and once you select 3, the sum of the values 0 plus 3 and it gives the value 3. So what we do, 3 is not equal to 15, it is less than 15. So we will go, it is a promising node, so go to the left from 3. So we have 3 plus 5, 8. 8 is also less than 15, so we will go. So similarly we are going to go on to the left by including A1, A2 and so on. On the right we will select the node and we will say that not including 3. So this figure represents the complete state space tree of the backtracking algorithm for the set 3, 5, 6 and 7 and the target equal to 15. So the root node is containing the sum as 0. Now when we include the first element A1 which is equal to 3, 0 plus 3 is 3. So in the left child we have the weight represented as 3. And the right side is without including 3, that is not including 3. We represent it as W/O, that is without 3. So now when you start from the first root node including 3, so the total is 3, 3 is less than 15, we continue. The next left child is including 5. So 5 when we include, 3 plus 5 is 8, so we write that 8 in the node. And the right child of this node we are having without 5. So similarly when you go to the next level, so we have included 3, we have included 5. Now coming to the next 6. 3 plus 5 is 8, we have written it. So 8 plus 7. So 6. So 8 plus 6, 14. 14 is less than 15. So we have to consider what is the remaining number, 7. When I add 7, 14 plus 7, it becomes greater than 15. So it is a non-promising node. So we backtrack. So when we come over there, we have 3 plus 5, 8. Now the option is without 6. So 8 we are having. So 3 plus 5 is 8 in that node. So without 6. So come back again in the node, we represent it as 8. Now 8 plus 7, including 7 on the left. So 8 plus 7 is 15. We have reached the solution. And then if we are going to find all possible subsets, then we have to continue. So backtrack, and from 8, now without 7, the value will be less than 15. So we will come back. And the next backtracking, we will come, and similar to this we will be finding all possible combination. So, the basic idea is, in the state space tree, the number which we write inside each node is equal to sum of the elements already included in the subset, represented by the particular node. So, the root node we have no element, so the value is 0. The left side with the 3, so once you add 0 plus 3 is 3, so write that weight as 3, the sum, and including 5 means 3 plus 5, 8, and then 8 will be having plus 6. So, 8 plus 6, 14, 14 plus 7 will go right like that. And when you consider in the next level where I am having the exact solution, so 0 plus 3 is 3, 3 plus 5 is 8, and then without including 6 you come, and then we add 7, so we have 8 plus 7, 15, which gives us the solution. So, we have the root node consisting of the sum which is equal to the target, the 15 means we are having the solution. Wherever we have x, it represents the pruning. The meaning is, the pruning stage we cannot have the solution. So, it is a terminal node, so we will come back. So, backtracking is needed wherever we have a non-promising node. Whenever we have a promising node, we will continue until we reach the solution here, which is equal to the sum of the target. So, we have now seen the procedure for performing this sum of the subsets. So, what we have done? We have recorded the value of S in the node. If S is equal to D, then we have reached the solution. If it is not 15, or here it is 15, so the general variable is D, and if we do not have D, then we can stop, or we can go back and identify the correct solution. If one solution is sufficient, we can stop saying that we have achieved the solution. So, we have the non-promising node condition checking by finding the sum of the values currently up to AI including, and the next AI plus 1 if I add, if it becomes greater than D, then you can say that it is non-promising because the sum is too large, or if all values, even if I add, it is going to be less than the D value, then we can say that the solution is not possible. So, we will backtrack. So, promising node we are having means the next child is going to be generated and the state is illegitimate, and you add it on the left. If it is a non-promising node, we should backtrack. So, finally, when you have a complete solution, if one solution is required, we can stop, otherwise we have to go for all possible solutions. So, with that, I thank you for your patient listening. Thank you.